So we are going to start the exercises on ring theory from this book, and this is the very first one from the first set of exercises. So here we have to provide two examples, one of a finite non-commutative ring and another of an infinite non-commutative ring that has no unity. Because we want non-commutative rings, so we can take matrix ring examples. The set of 2 by 2 matrices where the entries are coming from Z2 or Z2, which itself has the entries 0 and 1, is a ring under addition and multiplication of matrices. We know what matrix addition and multiplication of 2 by 2 matrices are, but still there is something else also that should be said. When we add two 2 by 2 matrices, then the sum looks like this. And when we multiply two such matrices, then the product looks like this: a prime plus bc prime, ab prime plus b d prime, ca prime plus dc prime, and cb prime plus d prime. We already know these things. Now, if these are ordinary matrices where the entries are real numbers, then this sum and, for example, this product, so these are ordinary sums and products of real numbers. So the plus and the multiplication that we have between any two entries, that are ordinary addition and ordinary multiplication of real numbers. But since here the entries of the matrices are coming from Z2, where we on this set we don't have ordinary addition and multiplication of real numbers, but in their place we have addition modulo 2 and multiplication mod 2. So if we are considering matrices from here, then although the forms of this sum and product are familiar to us, but the calculation that we have involving the entries, that should be interpreted in terms of addition modulo 2 and multiplication modulo 2. For example, if one calculates this product, which is the square of the matrix, all of whose entries are equal to 1. Considering these two as ordinary real matrices, that is matrices with real entries, then the result of this product, or rather this product, is 1 plus 1, 2. So all the entries are 2. Okay, but the same thing if you perform this calculation by considering this as a matrix from here, then 1 plus 1 is no longer 2 but 0. So in this ring, this is the correct calculation, not this one. Okay. So so when we say addition and multiplication of matrices, it is understood that the entries have to be manipulated using addition modulo 2 and multiplication mod 2, not ordinary addition and multiplication of real numbers. Okay, so that's the thing I wanted to say here. And then of course this is a statement which actually has to be proven. So it can be proven in much the same way one proves that 2 by 2 real matrices form a ring under ordinary addition and multiplication of matrices. Okay, so that we are not going to do, of course. It can be done. Now our focus is on showing that this ring that we have here is the two things we have to show. It is finite and it is non-commutative. Note that this is finite because this is finite, because there are only two entries. So the possible number of matrices that you can form, that is finite, because you have only so many choices for each of these entries in a single matrix. And in fact, if one wants, one can calculate the exact number. The set this has 16 elements. Why 16? Because the entries are, each entry has two possibilities. I mean, there are two choices for each entry, 0 and 1, and the entries are independent of one another. In this set, A, B, C and D just have to come from this set. Further, there is no restriction. We are not restricting these entries in any way other than the fact that they have to come from this set. So they are independent of, each choice is independent of the other three. So, and each one of them can be chosen in two ways. So there are 2 to the power 4 different possibilities. So 16 matrices will be there in this set. Also, for these matrices, we have if we calculate their product, then 1 times 0 is 0 plus 1 times 1 is 1, so 1. 1 plus 1 is not 2 but 0. 0 plus 1 is 1 and 0 plus 1 is 1. And this is not equal to the other product which we obtain by interchanging the matrices. This one is 0 plus 0 0 0. So the first row first column entries are different, so the matrices are different, but we have to complete the calculation. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. So our ring, besides being finite, is also non-commutative. Okay. Now the next example should be an infinite non-commutative ring, but also it should not have unity or identity. For that, we consider this set. Here M represents matrices and 2 is the size, the order of the matrix, 2 by 2 matrix. If you see M3 here, then the corresponding set will have 3 by 3 matrices. Here also we are considering 2 by 2 matrices, but the set from where the entries are coming, that is different. It is 2Z, the set of all even integers. A, B, C, D are even integers. So unlike the previous example, here the set from where the entries are coming, that set is infinite. This set again is a ring. Under addition and multiplication of matrices. This is infinite because the set of even integers is infinite. Or if you want to be somewhat more rigorous in showing that this set is infinite, you can identify a subset of this set which has the same cardinality as some non-infinite set. For example, you can consider this subset. This subset of M2 to Z has the same cardinality as the set 2Z, and you can see why. The map which links this matrix with this integer n is a one-to-one correspondence, and you know that this is infinite, So S is infinite, and because S is a subset of this, so this is also infinite. Okay, so the ring is an infinite ring. Now it is non-commutative. Is non-commutative because for these matrices we have to be careful to take even integer entries. We have, so we calculate the products. Okay, this time around the entries are ordinary real numbers or ordinary integers. So the addition and multiplication we have among the entries, that those are ordinary operations. So 2 times 0 plus 2 times 2 is 4, 2 times 2 plus 2 times 2, 4 plus 4 is 8, 0 plus 4, 0 plus 4, and that is not equal to the other product. This is 0 plus 0 0, 0 plus 4 4, 4 plus 0 4, 4 plus 4 8. Okay, so our ring is infinite and non-commutative, but besides that we also have to show that there is no unity. Contrary to that, we suppose that there is a unity, and then we arrive at some contradiction. Suppose there is a unity which is some matrix A, B, C, D in our ring. Then this product should give us this matrix back, because this has been supposed to be the unity. This implies, so what is this product? 2a plus 0, 2a, 0 plus 0, 0, 2c plus 0, 2c, 0 plus 0, 0. Or, so corresponding entries should be equal. 2a equal to 2, and why am I writing there? 2a is equal to 2 and 2c is equal to 0. Okay. this is not possible because A is an even integer. Since this matrix has been chosen from this set, so all the entries are even integers. So A is also an even integer, but from this first equation we see that A is equal to 1. 1 is an odd integer, so that is the contradiction. Hence our supposition is wrong, i.e. this ring has no unity, much like our society. So this completes the first solution. Then exercise 2. The ring zero, 2, 4, 6, 8 under addition and multiplication modulo 10 has a unity. Find it. Okay, the unity in this case, if one does all the calculations, is 6. I cannot actually use the dot here because dot has been reserved for something else. So what should I do? Let me just simply write like this. 0, 10, because if I write 0, 6, it looks or more confusingly, if I write 2, 6, it looks like 26. So 0, 6 is 0 and 6, 0 is also 0, although we should not, there is no need to write these two things because the operation addition modulo 2 and multiplication mod 2 are commutative, but still. So this is 0, then for that we don't actually, for these calculations there is no need to consider addition mod 10. Multiplication mod 10 is commutative, so these two things are equal. Anyway, so you can see that 2 times 6 is 12. Now 12 modulo 10 is 2, so that's why we have 2 here. So 4 times 6 is 24, 24 mod 10 is 4 because 20 plus 4. Then 36, 30 plus 6, so this is 6. There is no need to write that, is actually the same thing. And finally 6 times 8 or 8 times 6, since we are writing it that way, 48. So 40 plus 8, so that is again 8. Hence 6 is a unity in the given ring. Then 3. Give an example of a subset. Of a ring that is a subgroup. Under addition, but not a subring. And the solution, it's given in the text itself. Consider the subset where n is an integer of the ring are of real numbers, where we know that the addition and multiplication are ordinary addition and multiplication of real numbers. This subset, okay, this subset is, we will see, is a subgroup of R under addition, but it fails to be a subring. To see that it's a subgroup, we use one of the subgroup tests. Clearly, oh sorry, what am I doing now? This is, I am already writing the solution, so I was again writing another solution. So we have considered this subset. Clearly S is non-empty for n1 root 2 and n2 root 2 belonging to S, where n1 and n2 are integers. We have n1 root 2 minus n2 root 2 equal to n1 minus n2 times root 2 this also belongs to S. Why? Because n1 and n2 are integers, so their difference is also an integer. Hence, S is a subgroup of the group of real numbers under addition. Okay. Now the reason for S2 to not be a subring is this: it's not closed under multiplication. Note that this belongs to S because it is 1 times root 2 and 1 is an integer, but when we multiply root 2 with itself we get 2, and this does not belong to S. 2 does not belong to S because 2 is not of the form n root 2. And why is that so? If you suppose that 2 is equal to n root 2 for some integer n, then from this equation you get root 2 equal to n. Root 2 is a known irrational number, and n being an integer is a rational number, so that actually is not possible. If one wants, one can argue like this and make that argument a part of the solution, but we choose not to do so. Okay, this is so easy that one can see that 2 does not belong to S. So S is not a subring of the ring of real numbers, and this completes the solution. Then 4. Show by example that for fixed non-zero elements A and B, for fixed non-zero elements A and B in a ring, the equation Ax equal to B can have more than one solution. How does this compare with groups? Okay, so that means A and B are fixed non-zero elements. Oh, I forgot to consider the non-zeroness here. I have one solution, but here I have of course taken A and B both to be equal to 0. I forgot the non-zeroness here, so that means this solution will not work. So now I have to think of something. So we are in a ring, in some ring, where I want this to happen for more than 2 values of x. Okay. So that means what do I need? Say we have x1 and we have another x2 for which also this is true. Okay, x2, x1 minus x2 should be equal to 0. Okay. So that means this product is 0. So when do we have products? In many rings we have non-zero elements. When you multiply them you get 0. For example, in these 6 we have this equal to 0. Okay. Now this 3 can be written as what? 4 minus 1. So 2 times 4 minus 2 times 1 is equal to 0. So 2 times 4 is equal to 2 times 1, and both of them are equal to 2. 2 times 4 is 8, but when we divide 8 by 6, the remainder is 2. And 2 times 2 is of course, 2 times 1 is of course 2, which we divide by 6, the remainder is 2. Okay, yes. So that means if my A is 2 and B is also 2, then in place of x we can take 4 and 1. Yes, that is, we can give this example. In C6, if A is equal to 2 and B is also equal to 2, then both x equal to 4 and x equal to 1 satisfy the equation Ax equal to b. Let me see once more what I am saying is, does it actually make sense? 2 times 4 is 2, because that is 8, 8 modulo 6 is 2, and then 2 times 1 of course is 2. Yes. But what about this equation in a group? In a group for fixed elements. Oh, and that thing is also, the extra condition that A and B are both non-zero, that is also true, because A and B are 2, and in Z6 2 is a non-zero element. For fixed elements A and B, now in a group, unless the group is some sort of special group, non-zeroness has no meaning. Oh, but wait, non-zeroness has no meaning, but we can of course say that they are non-identities for two elements both different from the identity the equation Ax equal to B has the unique solution. X equal to A inverse B. Okay, so there not only do we have a solution always, but that solution is unique. Not BA inverse. Okay, don't make that mistake, because we don't know whether this group is abelian or not. In general, this is the unique solution. Then exercise 5, prove theorem 12(2), second theorem of our chapter 12. In this theorem, the statement is that there are two parts. The first half says that the unit element in a ring or unity in a ring, when it exists, is unique. There is only one unity when it exists. And when a ring element has a multiplicative inverse, that is also unique. Let R be a ring with two elements, 1 and 1 prime, acting as unity, that is A1 is equal to A is equal to 1A, and A1 prime is equal to A is equal to 1 prime A for all ring elements A. Okay. Our aim now is to show that 1 and 1 prime are actually the same thing. So what we do, we use these conditions, these equations, and we start with 1. Now you think of 1 in place of A here in the second equation. So 1 is equal to 1 1 prime, And now if you think of 1 prime in place of A here, then you get 1 prime is equal to 1 prime. So that's why 1 and 1 prime are equal. Should I have written it somewhat more elaborately, but you understand where this final conclusion is coming from. In the second part here, you put 1 in place of A, because since these equations are true for all elements A, so we can in particular take A equal to 1. So from there we get 1 equal to, not this part but the first part, 1 is equal to 1 prime. But then from here if we take A equal to 1 prime, which we can, then 1 prime also becomes equal to 1 prime. Next, let A belong to R, which has a, or we can, since we are writing the sentence like this, let A belonging to R have a multiplicative inverse. That is, A has some inverse. Now we will assume that there are two inverses and prove that they are equal. Let B and C be in R such that AB equal to 1, which is equal to BA. Note that multiplicative inverses can only exist when the ring has a unity. Otherwise, this equation will be meaningless. So that means we are assuming it's there in the background that our R has a unity, and that unity is denoted by 1. So AB is equal to 1, which is equal to BA, and AC is equal to 1, which is equal to CA. Our aim now is to prove that B and C are equal. Now B is equal to, in place of B we can write B1 because 1 is unity. Now in place of 1 we can write AC because AC is 1. Using the fact that multiplication is associative, this product can be written as BAC. Now from here BA is 1, so 1C, and 1C is equal to C. Hence the multiplicative inverse of A is unique. So this completes the solution and hence the proof of that theorem. Okay, the ink I am using right now, it has a very strong aroma, and this is creating a somewhat dizzying effect. The next one is exercise 6. Find an integer n that shows that the ring Zn did not have the following properties. That the ring of integers has what are the properties? A square equal to A implies A equal to 0 or A equal to 1. Ordinary conclusions to which we have become familiar. AB is equal to 0. When this happens, this implies A is equal to 0 or B is equal to 0. Then C, AB equal to AC and A not equal to 0 imply B is equal to C. Let me put some more ink. Yeah, the smell is extremely strong. Okay. And if I am remembering correctly, all the examples can be, or rather counter examples to these things can be found in C6 itself. So in C6, I have here the things. In C6, 3 square is 9. When we divide 9 by 6, the remainder is 3. And 3 is neither equal to 0 nor equal to 1. So in Z6, this thing is not true. Then B of course is very easy. In C6, 2 and 3 are different from 0, but their product is equal to 0. And finally in C6, so here we can have that example itself which we used today. 2 times 4 is 2 times 1, because 2 times 4 is 8. 8 modulo 6 is 2 and 2 times 1 is 2. So AB is equal to AC and A is not equal to 0, but 4 is not equal to 1. Okay, so these things which are normally taken for granted when we are dealing with ordinary real numbers or integers, they are not necessarily true in these finite rings, the n. Oh, I forgot to write one part of this exercise. Is the n, let me put it here, is the n you found prime? No, the n we have found, which works in all the 3 cases, is 6. It's not prime, and the reason is found in the next exercise. It cannot be prime, because when Zn, their n is prime, then in that type of ring these properties again are true. Exercise 7. Show that the 3 properties listed in exercise 6 are valid for set P or ZP where P is a prime. Now the thing that makes these properties true in a system is the existence of multiplicative inverses for non-zero elements, which is true for real numbers. So that's why these properties are true when we have the things here A, B, C as real numbers. But in Z6, every element does not have a multiplicative inverse. 2, for example, does not have a multiplicative inverse, which you can verify directly because there are only 6 elements in Z6. You will see that no element of Z6 acts as the multiplicative inverse of 2. But in this type of rings where the P is a prime, inverses exist, and we are going to use that fact to prove these properties. We know that for any, what should I write, any m belonging to Cp, you know what this m is. It's an integer from 0 to p minus 1. There exists an element M inverse belonging to CP. What exactly this M inverse is in terms of M, that does not matter. Only its existence is enough for us, such that M inverse equal to 1 equal to M inverse M. Okay. Now we prove those three things. We now prove the properties listed in exercise 6 below. A. Let A be an element in CP such that A square is equal to A. Okay, if A, so what is it that we have to prove? We have to prove that either A is 1 or 0. So if A is already 0, of course there is nothing to prove. If A is equal to 0, then we are done. So assume A is not equal to 0, but then its multiplicative inverse will exist. Then A is equal to A1. Okay, we can, in place of A, we can write A1, because in ZP A1 is again A1 is the unity. And now in place of 1 we can write A inverse. Use the associative law for multiplication. You have A inverse. A is A square. Now use this relation. A square is A. So this is equal to 1. So that's how you prove that when A is non-zero, it has to be equal to 1. So either A can be 0 or 1. So this proves property A. Then in property B, let A and B belong to CP such that their product is 0. Again, like before, if A is 0, then we are done. So assume A is not equal to 0, then its inverse, multiplicative inverse exists in CP. Then B is equal to AB is equal to 0. So that means okay, AB is equal to 0. So okay, so that means I have to take 1 on this side, 1B. Now in place of 1 we can write A inverse A, because that is also equal to 1. Again use associative law of multiplication and have this product. Now AB is given to be 0, and we know we have those properties in this chapter itself, which say one of those elementary properties in a ring say that if you take the product of any ring element and 0, then you get 0. So this is equal to 0. So either A is 0, or when A is not 0, B must be equal to 0. So this proves property B. And finally, in property C, we have this. Let A, B and C be 3 elements in CP such that AB is equal to AC and A is not equal to 0. Then using elementary ring calculations, from this equation we get A times B minus C equal to 0. Now in property B, we have already proved that when the product of two ring elements is 0, I mean here in this ring, not in any ring, then one of them must be 0 at least. Now it is given that A is non-zero. So by property B, proved above, B minus C must be equal to 0 or B must be equal to C. So this completes the proof of property C. Then 8. Show that a ring is commutative if it has the following property. That AB equal to CA implies B equal to C when A is not equal to 0. If there is a ring in which you take 3 elements A, B and C such that A is not equal to 0 and AB is equal to CA, then it implies that B is equal to C. If this is true in a ring, we have to prove that the ring is commutative. Let R be a ring with the given property. Let A and B be any elements in R. Our aim is to show that AB is equal to BA. If A is equal to 0 or B is equal to 0, then of course AB and BA are equal and both of them are equal to 0. So in that case the two products are equal. Now assume both A and B are non-zero. Okay. Since multiplication is associative, A times BA is equal to AB times A. Okay, now look at this equation. This equation looks like AB is equal to CA, where capital A is A, B is BA, C is AB, and again capital A is A. And A is not equal to 0 because we have now assumed that both A and B are non-zero. So by our hypothesis that the given property is true in R, B must be equal to C, that is these two things must be equal. BA must be equal to AB. Since A is not equal to 0, our hypothesis implies BA is equal to AB. Therefore, R is commutative. So that's the solution. 9. Prove that the intersection of any collection of subrings of a ring R. Of a ring R is a subring of R. We will apply the subring test. Let S alpha belonging to say A, B, an indexed family of subrings of R, which is actually any collection of subrings of R. Index family means we are indexing or labeling the subrings in this collection using some index set A, where for each alpha in A there is a subring S alpha of R. Sub A, the subrings of R, where A is a non-empty index set. Non-emptiness of A is needed because we are going to consider the intersection of all the elements in this family. If we had to consider union, there although an empty collection will not give you anything, the union will also be empty, but the intersection of an empty collection is not well defined. In some texts it is considered to be a universal set, but it's not well defined, or it's not needed also. Okay, so we take A to be non-empty. Or if you find these things somewhat confusing, mention of indexed family and index sets, you can just simply consider a collection, some collections S, whose elements are subrings of R, and this is a non-empty collection. That's all. In fact, that's what we are doing here. Let B be the intersection of the S alphas. We now have to prove that B is a subring of R. The first thing we need to make sure is that B is non-empty. Since 0 belongs to S alpha for all alpha belonging to A, because each S alpha is a subring, each one of them will have the 0 element of the ring. So the 0 will belong to their intersection also, that is in B. So B is non-empty. Now let B1 and B2 be two elements in B. Then B1 and B2 belong to S alpha for all alpha belonging to A, because B is their intersection. Since S alpha is a subring of R for all alpha belonging to A, we have B1 minus B2 belonging to S alpha and B1 B2 also belonging to S alpha for all alpha belonging to A. Okay, this is because each S alpha is a subring. So B1 minus B2 belongs to all the S alphas and B1 B2 also belongs to all the S alphas. So B1 minus B2 belongs to their intersection, that is B, and B1 B2 also belongs to B. Thus from the subring test, B is a subring of R. And we will solve one more. 10. Verify that examples 8 through 13 in this chapter are as stated. Okay. In example 8, it is stated are subrings of R for any ring R. So to verify this, you just have to apply the subring test. Note that this has only one element, the 0 element is non-empty, and since 0 is the only element, so 0 minus 0 is again in this, and 0 0 is also in this. So this is a subring of R. Next, all these things look too much ado for nothing. I mean, it seems like we are becoming formal just for the sake of writing formal solutions. That is true, but since we have other examples also which are not this obvious, so we stick to one kind of writing, I mean the solutions. Next, R itself is non-empty, and for any elements R1 and R2 in R, we have R1 minus R2 belonging to R and R1 R2 also belonging to R. So R is a subring of itself. So that is example 8. Then in example 9, it is stated that (0, 2, 4) this set is a subring of C6 and 4 is a unity. Since so we have to form all the differences and all the products and see that they again belong to this set. Zero times anything is 0. Comma we have written the product before writing the differences. I think it will be better if we write the differences first and not in this fashion also, not starting with since. Note that (0 minus 0) which is equal to 0, 0 minus 2 is 4. Our calculations are happening in Z6. 0 minus 4 is 2. Okay, then 2 minus 0 of course is 2. 4 minus 0 is 4. What else? So these are all the differences where there is at least one of the elements is 0. Now we come to non-zero elements. 2 minus 2 is 0. 2 minus 4 is minus 2. Minus 2 means 4. Okay. Then 4 minus 2 of course is 2, and 4 minus 4 is 0. Are all in this set. Have all the possible differences been taken into account? 0, then 0, 2, 2, 0, 0, 4, 4, 0. Okay. Then 2, 2, 2, 4, 4, 2, 4, 4. Yes. Also, since multiplication mod 6 is commutative, unlike the differences, when we calculate the products, we don't have to calculate the two products AB and BA separately because they are going to give us the same thing. Okay. 4 times 4 is 16. Hmm. 2 times 4 is 8, modulo 6, that is 2. All belong to hence and from these products you can see that 4 is a unit element or 4 is a unity. Why? 0 times 4 is 0, of course. 2 times 4 is 2 and 4 times 4 is 4. So you multiply anything with 4, you get that thing back. So 4 acts as a unity. Okay, so that is exercise 9. Example 9. In example 10, it is stated that for each positive integer n, the set nz or nz, which consists of all the multiples of n, all the integer multiples of n, is a subring of the ring of integers. Clearly, the subset we have here is non-empty. Now for any integers a and b, we have NA minus NB equal to n times a minus b. Since a minus b is also an integer, so this belongs to NC, and NA times NB, it can be written as n times NAB. NAB is also again an integer, so this belongs to NC. So this is a subring of the ring of integers. Then in example 11, it is stated that the set a plus bi where a and b are integers of Gaussian integers is a subring of the ring of complex numbers. We have non-emptiness is obvious, and for integers a, b, c, d, a plus bi minus c plus di equal to a minus c plus b minus d times I. So because a, b, c, d are integers, so a minus c and b minus d are also integers. So this belongs to this. And what do we get when we multiply them? AC minus BD plus AD plus BC times I. Again, because A, B, C and D are integers, so AC minus BD and AD plus BC are also integers. Hence, the Gaussian integers form a subring of the ring of complex numbers. Two more are left. In exercise 12, we have the ring R of all real valued functions of a single real variable. That is the kind of functions we encounter in calculus or real analysis of a single variable. Functions which look like this. Okay, now the set of such functions forms a ring under a pointwise defined addition and multiplication. Under pointwise addition and multiplication. What this means is this. Suppose you have since the domains of these functions have not been restricted, so we can consider that they are functions like this. Say f and g are two such functions. Then by their sum we mean this function f plus g, which is defined like this. F plus g at x, where x is some real number, is defined to be equal to f of x plus g of x. Note that this plus is ordinary addition of real numbers, because f of x and g of x are real numbers. That's why we need real valued functions, where the outputs of these functions are real numbers, so that this sum makes sense. And since we are defining this addition pointwise at each input or each point, so hence the name pointwise addition. Like that, you can define the product of these functions to be the function such that the image of any real number under that function is the product of these two real numbers, f of x and g of x. This is also defined pointwise. Under this addition and this multiplication, the set of all functions which are like this, which have domain and range both equal to R, they form a ring. It's that ring R we have here. Okay, and we have this subset. And S is the subset of R consisting of those functions whose graphs pass through the origin. That is, S looks like this. S consists of those functions from R such that f of 0 is equal to 0, because then only the graph of y equal to f of x will pass through the origin. 0, 0 is a point on the graph. Now we have to prove that this S is a subring of R. Same procedure. First you make sure that S is non-empty. That is rather easy. Note that the identity function f from R to R given by you can take the identity function or the constantly zero function or any other function whose graph passes through the origin. Note that the function given by fx equal to x in R is such that obviously f of 0 is equal to 0. So f belongs to S and hence S is non-empty. So then we have to prove that S is closed under subtraction and product. Since we have already used f to denote this function, so we take some other functions g and h, any two functions in S. Then you can also express these equations by saying that g and h vanish at the point x equal to 0, and hence what is g minus h of 0? This is g of 0 minus h of 0. And gh of 0 this implies g minus h belongs to S and gh also belongs to S. Thus S is a subring of R. And finally we have example 13. In example 13, we have the ring R of 2 by 2 matrices over the integers under addition and multiplication of matrices under addition and multiplication of matrices, and the subset, no name is given to this subset, but let us call it S, is 0 0 P of subset of diagonal matrices. again we have to prove that S is a subring of this. We have definitely S is non-empty. For two such matrices, first of all, their difference is again a diagonal matrix, because A minus C 0 0 B minus D, this belongs to S. And what about their product? Diagonal matrices are the simplest type of matrices to work with. We will see why when we study linear algebra. From the multiplication itself, you can see that things are particularly simple. AC plus 0 is AC. Is the 0 plus 0 is 0, again 0 plus 0, 0, 0 plus BD, BD. So to multiply these two matrices, you just have to multiply the corresponding diagonal entries, that's all, AC and BD. So this is again a diagonal matrix, this belongs to S. Hence, S is a subring of R. So we have verified that all the examples from 8 through 13 are actually, whatever we stated in those examples, that are actually true, all of them. So I end the video here itself. We will see more exercises and their solutions in the coming videos. So this time we have ring theory, we have solved ring theory problems. The next video on Gallian will be group theory, and then we will alternate between rings and groups like this. So if you want to say something on these things, you can comment in the comment section below, or you can mail me here. So see you in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice night and stay safe.